Hello everyone. This video is to present a groundbreaking antenna published on IEEE TAP. To begin, let's consider the application scenario. When satellite operates in low Earth orbits, a flat top beam provides uniform coverage over the Earth's surface. When in higher altitudes, an Isoflux beam ensures consistent illumination on the curved terrain, and a pencil beam offers focused energy for high data rate transmission in any Earth orbits. The structure consists of a circularly polarized feed antenna and a 3D printed dielectric container that has 3 independent cavities for holding liquid dielectric. By selectively filling these cavities with a liquid dielectric, the antenna controls the aperture field distribution to switch patterns. For instance, filling zone 1 produces an isoflux beam, zones 1 and 2 yield a flat top beam, and all 3 zones create a pencil beam. Next, let's look at the working principle of isoflux beam. By controlling the height of the dielectric too, the phase difference between point A and B can be controlled. The right figure evident that as H increases, the central gain of the radiation pattern rises. At H equals 16 mm, the antenna shows the ideal isoflux beam. Step 2 presents the final optimized structure for a wider operating bandwidth. The next is the realization of flat top beam. The figures illustrate the relationship between the circular aperture distribution in a spherical coordinate system and the far field radiation pattern. When the first out of phase is slightly diffused to either side, the resulting far field pattern will manifest from isoflux beam to a flat top beam. Utilizing this principle, we loaded a red-colored liquid dielectric 3 to control the phase of the aperture field. It can be found that the suitable H4 and R5 can achieve the isoflux beam to flat top beam. The following section covers the pencil beam design. We loaded a hemispherical liquid dielectric on the structure. This entire liquid dielectric acts as a converging lens, focusing the spherical electromagnetic waves radiated from the feed. The simulation results for the pencil beam are presented. To verify this design, the antenna was fabricated and measured. The simulated and measured reflection coefficient remained below, -11 dB, between 4.6 GHz and 5.2 GHz. The peak gain of the pencil beam mode is 10.7 dBIC. The peak gain curves of the isoflux and flat top beam modes exhibit a similar trend, reaching 5 dBIC at 4.9 GHz. Next is the radiation patterns and space axial ratio of the proposed 3 modes. At isoflux mode, the peak angles of the radiation pattern are plus or minus 35 degree. At flat top mode, the 1 dB beam width is plus or minus 38 degree. At pencil beam mode, the 3 dB beam width is plus or minus 18 degree. In the coverage area where the pattern works, the corresponding space axial ratio range is all below 2 dB. The overall measured results of the antenna align well with simulations. The comparison table shows that the existing pattern reconfigurable liquid antennas are predominantly linearly polarized. In contrast, the proposed antenna introduces 3 reconfigurable beam shapes with circularly polarized, a novelty not found in previous work. Its simplicity, low cost, and adaptability make it ideal for future communication systems, from satellites to IoT. Thank you for watching.